On the third rock from a random star, we humans create, invent, and push the frontiers, but now pay a high price for the energy. Our dependence on fossil fuels leads to an alarming excess introduction of carbon dioxide into the atmosphere, creating serious threats to our biosphere and our lives. Often, concerned citizens see renewables as the answer to this global challenge. Frequently, they also see nuclear energy as something dangerous that must be phased out. However, neither of these strongly held beliefs is based on good science or arithmetic. We need to look at the facts. Seeing ourselves as profligate consumers of energy and other resources, and wishing to make a difference, we also imagine that we can have a significant effect on the situation through conservation. This graphic illustrates that if the U.S. reduced its energy consumption in half, which will never happen, and the rest of the world used energy at that same reduced level, we would need to more than double the energy consumption in the world. CO2 pollution is an urgent challenge, but so is widespread deep poverty, largely dependent on lack of ready access to energy for the supply of water, sanitation, health care, and basic amenities. As the population expands and the vast majority emerges from poverty, we will have to produce much more energy, not less. Conservation is moral. We should always practice conservation, but conservation has very little to do with solving the global energy crisis. Another look at this reality. North America is the tall bar on the left. That many people use that much electricity per person. Next is Europe. All the rest of the world is below that European standard. All of the people in the last 3 blocks, 10 times the North American population, are subsisting on 85 watts of electricity or less, while we use 1,500. It's not reasonable to say in any sense that we're going to solve the problem by reducing the energy consumption in the world. It's not going to happen, it can't happen, and it shouldn't happen, because these people want and deserve clean water, sewage systems, basic electricity, infrastructure, and a washing machine. This shows the strong linear correlation between energy and prosperity. Here we see a really dramatic and interesting nonlinear correlation between that energy-induced prosperity and population. If you get above a certain level of income, the birth rate drops precipitously. Above this level, it falls below 2.3 children per woman. That's a stable replacement rate. Again, reduction in global energy usage is a non-starter. We're going to have to add a lot more energy to meet our moral responsibility to other people on this planet. So much for conservation. It's virtuous, but it's not the answer to this problem. Back to renewables. In spite of recent improvements, renewables are, in fact, technologically backwards. That wouldn't really matter if they were the only solution available and if they could solve the problem. However, they can't solve the problem. Furthermore, they cause significant environmental damage, and if we commit ourselves too much to them, we will delay the real solution. Why do I say renewables are technologically backwards? As we moved into and through the Industrial Revolution, we found it preferable and ultimately necessary to move away from windmills and water wheels to something more serviceable. The new basis of energy production established a better foundation with key characteristics. We use compact energy-dense fuels. We use compact conversion machinery. We can turn our power on instantly at full tilt anytime we want, and we can locate our power anywhere we wish. You can't do one of those things with either solar or wind. Of course, the problem with this has been the toll from pollution, which is what we all want to address. More of the numerous problems with renewables are listed here, but the punchline is this. The fossil fuel industry laughs all the way to the bank. Critics describe large solar farms in the Southwest as decorated natural gas plants because that's what they really are. Because of their irregularity and undependability, their really low capacity factors, such farms need quick-acting baseload backup. The only backup that works well for this is natural gas, which emits large amounts of methane, a terrible greenhouse gas, in addition to CO2. This effect gets worse the more that these systems penetrate the grid. An enormous deficit of renewable technology is the excess use of material. Solar, photovoltaic, and wind both consume large amounts of concrete, steel, and other materials. Conventional nuclear is minuscule by comparison. Modern nuclear will be a fraction of that. Preparing the foundation for a wind turbine. Huge excavation, concrete skim, tons of rebar, tons of concrete yet to be poured, in hopes of preventing this. Disposal of turbine blades after their relatively short lifetimes. Glass-filled thermoset materials which are not easily processed or recycled. Note the size of the bulldozer. Not only valuable materials, but too much land. Yes, cows can graze beneath the wind turbines, while they slaughter endangered bats and large birds. But the land required is not trivial, nor the creation of access roads and power lines. Is this environmentalism? This shows the recent growth in wind turbine size. The popular Jacobson roadmap proposes the installation of 500,000 of the giants of the bunch, with swept area bigger than a 747. Another piece of the roadmap, the Massachusetts page. It's striking. 55% of our energy, that's not just electricity, that's electricity, transportation, manufacturing, 55% from offshore wind, from those enormous turbines out in the ocean. I suggest that that's not politically, economically, technically, or environmentally possible or advisable. This is what happened in Germany. They responded to Fukushima by closing nuclear plants and installing a lot of solar and wind. This is the installed capacity for wind. The blue spiky stuff is what you really get out of that. Now, not only is that spikiness a big problem for the grid, but you have to even it all out with something else. What's that something else? It's increasingly coal. In France, where they get most of their electricity from nuclear, they have the cleanest air in Europe, and their electricity costs half of what it costs in Germany. Meanwhile, Germany's air is getting dirtier because they're burning more coal, and the cost of electricity is going up. Environmental damage. This can be done in a better way, but this is what's happening right now with the manufacture of solar panels. The Chinese father says, "It's poison air, you have to stay inside." In the soil around his home, silicon tetrachloride, chlorine, hydrochloric acid, nothing grows. And the manufacturing executive says, if it happened in the United States, you'd probably be arrested. This is all because there's a lot of very caustic material in the manufacture of solar panels. Then one day we're going to have to recycle it. That's a lot of square feet and a huge volume. Solar panels, and this may sound incredible, 300 times more waste on a weight basis than nuclear reactors providing the same amount of energy. This is what happened to a solar farm in Puerto Rico when Hurricane Maria came through in 2017. This is one small piece of the solar farm. Solar panels typically contain glass, silicon, lead, cadmium, tellurium, even radioactive indium. Fragments of these solar arrays now leach into the soil. And hurricanes are going to strike solar farms again. Even if the hurricane doesn't come, you are going to have to dispose of all of that material in a maximum of about 40 years. Then you have to start all over again. Conventional power plants, whether they use fossil fuel or nuclear fuel, last for double that. When confronted with the undependability of renewables, a common response amongst proponents is that we will just use batteries or some other form of backup. This is just hand-waving. There is no such solution on the horizon. The largest battery storage center in California. It would take over 15,000 of these and $750 billion to provide 4 hours of backup for the U.S. grid. The current old-fashioned grid has on the order of 150% above average usage level of dispatchable capacity at all times without storage. The necessary increase in lithium mining and production would be off the charts. What's the penetration of renewables? 2019 U.S. Hydro and geothermal are specifically site-dependent. Hydro is near max penetration and declining. The only truly green source that can grow to provide baseload power is nuclear. Nuclear is also the only candidate that can expand at some reasonable cost in time, money, and material. Okay, that was quite an attack on renewables. It also just scratched the surface. Is there an alternative? Yes, it's nuclear. Let us consider the potential, the fears, and the future. The potential is huge. If you look at any kind of chemical fuel, going from sugar to gasoline, you're talking about 20 to 50 megajoules per kilogram. Uranium has 76 million. This is not a potential to be summarily rejected just because we're too scared. What we're scared of is not metaphysical, it's physical. As with other technologies, petrochemical, pharmaceutical, food processing, we have figured out how to deal with accompanying risks, and today nuclear plants operate very safely. What are the fears? Radiation, waste, and proliferation are the big ones. First, radiation. This shows your lifetime exposure to radiation. 82% of it is from the environment, and you're getting it right now. You're getting it from the ground, and you're getting it from the sky. Inside all the cells in your body, DNA strands are being broken, but exquisite intracellular machinery has evolved to repair the breaks as they happen. The only time you really get damaged by radiation is if you get way too much of it in a short period of time. Such exposure from a commercial nuclear power plant has never happened in this country. The remaining 18% of the radiation you will receive, expanded on the right, is diagnostic X-rays, radiation treatment for cancer, and consumer products, including smoke detectors and exit signs. What about waste? This is what's left after the closing of nuclear plants like Pilgrim. These are concrete dry casks, air-cooled, nominally slated to go to a central repository, yet very safe and secure as they are. So-called nuclear waste, which is mostly partially consumed nuclear fuel, is not a supernatural monster about to grab you by the ankle. It's just physical material which can be physically secured. This material can be reprocessed to supply more energy, and some of the fission byproducts can even be put to good use. The remaining material can be vitrified and safely sequestered. The waste issue is actually an argument for nuclear, since it is the only energy-generating technology that secures all of its afterproduct, and the quantity is minuscule compared to what is generated by other technologies. What's in there? As used in the reactor, uranium oxide pellets in zirconium tubes bundled together hung in the water. The pressurized water goes past, removes the heat, moderates the reaction, which means slows down the neutrons so that the reaction can take place, and delivers that heat to the energy generating system. This shows the isotopic content of natural uranium as it comes from the Earth. Only 0.7% is the fissionable isotope uranium-235 needed for nuclear energy or for nuclear weapons. The 7 out of 1,000 atoms shown in yellow. To produce usable fissionable material, we have to enrich the uranium, which is not easy because all of the atoms are the same chemically. Today, centrifuges are the technology of choice. To fuel a conventional water-cooled reactor, we need to enrich to at least 3%, usually not above about 5%. To make a bomb, you need to go above 80%, which is why the fear that a nuclear power plant can explode like an atomic bomb is nonsense. It's physically impossible. By the way, the Canadian CANDU heavy water moderated reactors can use unenriched natural uranium. What happens inside? A neutron breaks up a uranium-235 atom into two fragments. You might notice they're different sizes. This releases additional neutrons and a large amount of energy. Inside the fuel rod, as this happens, it gets extremely hot and gaseous fission products build up, leading to cracks in the uranium oxide fuel. The gases also pressurize the tube, and one of these gases, xenon-135, is a neutron hog, so it starts to quench the reaction. All of this means that the fuel rods have to be removed prematurely from an energy availability standpoint. Thus, what we remove from the reactor is not primarily waste, it's just partially spent fuel. In spite of their technical challenges, legacy reactors are serving us safely and well. What is exciting today is that there's an even better way to go, and by that I mean a better way to go than these solid-fueled, water-cooled reactors. Dozens of companies are now working on new nuclear. The majority of the designs are for so-called small modular reactors, which can be built in a factory and delivered by truck for below-ground installation at a fraction of the cost of conventional reactors. A special subset of these SMRs are molten salt reactors, and one of them that is particularly exciting is the thorium-fueled molten salt reactor. The molten salt reactors are small modular walk-away safe reactors. No hydrogen explosion, no steam explosion. They have wonderful features. And we did it already. We did it for 5 years in Oak Ridge. On the left, scientists putting together graphite logs, which will be the moderator. They go into the reactor can on the right. The can goes into a silo, which is covered with a thick shielding lid. Clearly visible are the heat exchanger and circulating pump. Here are some visitors you might recognize. The scientist in the center, Alvin Weinberg, was the head of that effort. He has written a compelling autobiography about all of this. What is this? It's the simplest of reactors, often called a pot, a pipe, and a pump. It's filled with a melted mixture of 2 carrier salts and a third salt of fissile material. All the complexities of a water-cooled solid-fueled reactor are eliminated. No possibility of steam or hydrogen explosion, and walk-away safe. Easy to refuel online and remove fission products during operation. Also capable of much higher temperature, which opens numerous new possibilities and applications. There are several serious efforts underway to bring this technology back to life and into public service. One U.S. company, Thorcon, is already in agreement with Indonesia, which is a country in great need of more energy, to build these barge-style reactor islands that will settle into a special pier. They will be served by a special can ship, which will bring in small sealed reactor cans, which will be transferred into the barge-style power plants, where they will run continuously for 4 years, then cool down while a second onboard unit is swapped into service. Finally, the reactor cans will be returned to a central reprocessing and refueling facility. This company, Terrestrial Energy in Canada, is well along in its technical, financial, and regulatory pathway. They have a very strong company, and their first reactor is slated to be up and running in this decade. Again, you've got a factory-manufactured reactor being brought in by truck, put into a silo. Run it for 7 years, turn it off, turn a second one on, let the first cool down, and then you can either go into long-term storage or you can reprocess the fuel. A quick contrast with conventional nuclear plants. In the cross-section on the left, the small glowing part is the reactor. The huge rugged building surrounding it serves as the containment structure. The reason it's so enormous with conventional nuclear is that in the reactor core, water is pressurized to 160 atmospheres. If it does go to steam, if you do have that kind of an accident, you need this much volume to contain it. On the right, one of these plants being constructed. Here is a comparison between an expensive conventional legacy reactor and a modern small modular reactor, totally below grade. Finally, a quick look at the potential of thorium. Thorium is not fissile, it's fertile. Uranium is element number 92, thorium is element number 90. It will absorb neutrons in an appropriate reactor, and then by beta decay, it will turn into that other fissile uranium isotope, U-233, which is actually a better fuel than U-235 for various technical reasons. And now we have a new fuel. This is a breeder reactor, so new fuel is created continuously. Thorium is 4 times as abundant as natural uranium, therefore hundreds of times more abundant than U-235, which is the fuel that we use in conventional reactors. Its energy potential is so great that this 6-kilogram ball of thorium is equivalent to 230 train car loads of coal. That beach ball would supply a 1 gigawatt power plant for a year. Because they operate at much higher temperatures, molten salt reactors produce electricity more economically. The high temperature means we can do other things now too. We can desalinate water, synthesize liquid fuels, and for the first time provide industrial heat. The dense potential of nuclear energy can eliminate the burning of fossil fuels and alleviate poverty. The big roadblock is not technology, it is fear. May we concerned environmentalists overcome our fear and stand in the vanguard. Here are a few sources for more detailed information. Thank you for your attention.